Hello again. This is video lecture 22.2, and we're going to discuss section 3 in chapter 22, pardon me, where we look at the electric field of a particular important charge configuration known as an electric dipole. Now, I briefly mentioned an electric dipole in the previous video lecture, but let's say again what an electric dipole is. An electric dipole is 2-point charges, one positive, one negative, equal magnitude of charge, separated by some finite distance. So look at this picture down here in the lower left corner. You've got a point particle with charge, let's call plus q, and a point particle with equal but opposite charge, negative q, and they are separated one to the other along a straight line by some distance we'll call d. That configuration is called an electric dipole. Pole is a fancy word for a single point charge. Dipole means 2 point charges. This is an electric dipole. You can see already down here in the lower left drawing the electric field line representation of the electric field created by a dipole. And that's an important configuration. So we want to kind of have a general sense of that field and what it looks like. Note where the field lines are bunched up in the region between the particles, the field is strong. And it does some curving here, kind of along this perpendicular to that line, the midline through there, and so forth. And yes, it does continue. Like see this field line right here? It actually goes out, curves around, and is that one coming back in. They all do that. They all start on the positive charge, go out, curve, and come back in, and terminate on the negative charge in an electric dipole like that. All right, so you can see a couple of places, by the way, well, a place where the authors have picked a point, like right there, and have sketched the electric field vector there. Remember, the electric field vector in a field line diagram is tangent to the field line that passes through that point in the direction of the arrow on the field line. So that is right like that. That's the E arrow at that location. What if we picked a point up this way, up above? By the way, this line, let me draw it with a dashed line. This straight line that passes up through both charges is called the symmetry, the dipole symmetry axis. The line going through them both. So I've picked a point there on the symmetry axis. What would be the direction of the electric field there? Well, the field line that passes through that point is going straight out and points this way. So the electric field vector E arrow there would point roughly like that. All right, now calculating the actual electric field at any given point is somewhat complicated here, but there are 2 main directions that are worth focusing on. There's along the symmetry axis and finding the field along there, and then it's not too bad to find the electric field along the perpendicular bisector, that line. But we're going to spend our time here focusing on finding the electric field on this symmetry axis, on the line going through them both. And in fact, we're going to limit ourselves to points on that symmetry axis that are far away from the charges. What does it mean by far? Far compared to the distance d. Remember, d is the distance between the 2 charges. Why is that so important? What's so important about being far away from the dipole? Well, it turns out that many important molecules are electric dipoles. And therefore, when you want to study the behavior of multiple molecules in a combination or a solution, you need to know the electric field that one molecule is creating and that the other molecules are immersed in. But molecules are small, and the other molecule may be quite some distance away compared to the distance d we're talking about in the molecule. So you're almost always interested in when you're far away from the dipole. Okay? All right, so we're going to find the electric field on the symmetry axis and far away from the dipole. So now I want to look at the picture on the right. I know there's a lot going on, but it's going to help us do this calculation. So there are the dipoles, the charges in the dipole. There's the plus charge, plus Q, and then there's the negative charge, minus Q. They've also marked with just a dot the center of the dipole. Let's take that to be the origin. Okay, that's the origin, the center of the dipole. And the distance between the dipoles is d, as denoted here. Okay, now we've picked a point P. I'm going to mark it with an X. There's no actual charge up there at point P. It's just a point on this symmetry axis. We're going to call the symmetry axis the z-axis. And we want to find the net electric field there. Okay? Well, there's a contribution to the electric field at point P from each of those charges that make up the dipole. We got to find those two contributions as vectors and then add them. All right. So we're going to label the distance from the origin out to point P as a distance z, because it is on the z-axis. Then the distance from the plus charge to point P, right there, this book labels r sub plus, the distance from the plus charge to point P. And the distance from the negative charge to point P is that distance. And this book labels that r sub minus. And then it also shows the contribution of each charge's electric field at point P. The positive charge is closer to point P, and so it creates a larger electric field that points away, like that, right? Because the field from a positive charge points away from it. And they call that E plus. That's a contribution to the total field from the plus charge. Now the contribution to the total field at P from the negative charge, first of all, will be smaller in magnitude than the contribution from the plus charge. You see why? Because the negative charge is farther away from point P. And it points in the negative z direction. Do you see why? Because the contribution from a negative charge for the field points towards the negative charge. So that's this arrow right there that the author labels E minus. So what we have to do here is add the vector E plus to the vector E minus. Since they point in exactly opposite directions and the E plus one is larger, I can already predict that the net field will point upward and be roughly that big, roughly. Okay? But we've got to find the formula for calculating that net electric field. All right. Okay, let's go through the math for doing that. I'll start here and work my way down on the right column, but I'll start right here. That equation you see right there, finally, by the way, is the final answer that we're going to get. But we got to get there. So we're going to find the total electric field at point P by adding the contributions that we have labeled E plus and E minus. That's vector addition, so it's a plus. We'll account for the different directions here in just a second. Let me now write down the symbolic expression for E plus. Electric field of the plus charge. That's the electric field of a point charge. We know how to write that now. You take the size of the charge, Q, over 4 pi epsilon 0, and what we were calling r squared. But in this case, that would be r plus squared, right? That's the distance I need to use, right there. And now let's get the direction. E plus points in the plus z direction, so it's plus k hat. Now I add to that the vector E minus. I need the magnitude of that charge. Notice the magnitude would just be Q over 4 pi epsilon 0. And now I need the distance they call r minus squared, which is this distance right here. But now the direction is downward. So that's negative k hat. Okay, so now next line, let me factor out front a q k hat over 4 pi epsilon 0. Then I have 1 over r plus squared minus 1 over r minus squared. All right, now I'm going to say a little bit more about the r plus. All right, now here comes something very important. R plus, let's get rid of some of the extra stuff, okay? All right, that's good for right there. I'll get rid of that too. Okay, R plus is that distance right there that I've got listed. Here's how I'm going to denote it. R plus is equal to the z value minus that distance right there from the origin to the plus charge, which is d over 2. So R plus is actually z minus d over 2, and I have to square that quantity. Okay, that's 1 over r plus squared. Then I've got minus 1 over r minus squared. Okay, now let me focus on that one. Remember, r minus is from there to there. Note that that's the distance z plus that distance right there, which is, again, d over 2. So this is z plus d over 2 quantity squared, close bracket. Okay? All right, now here's the next thing I'm going to do. I'm going to do that right up over here. E arrow equals qk hat over 4 pi epsilon 0. I'm going to factor out of the denominator, it might seem odd at first, a z squared. What that leaves me with, move this over, is 1 over 1 minus d over 2z quantity squared minus 1 over 1 plus d over 2z quantity squared. Okay, I factored a z squared from each binomial in those denominators. And that's why there's a z squared out front in the denominator. Then the binomials look like that. So now, here's the next little trick. Each of those binomials in the denominator can be brought up into the numerator if I change the exponent from 2 to negative 2. Minus d over 2z to the minus 2 minus 1 plus d over 2z to the minus 2. Okay, now we're looking in a special limit. And here it is over here written. The absolute value of z is much, much greater than d. That means these little fractions right here, d over 2z that appears there and there, they're both very small compared to 1. They're much less than 1. Each of them is the same. So what I really have for each of those is a binomial of the following general form. 1 plus, I'll just use the generic symbol x, and the power is a generic n, where the x here stands for either d over 2z or negative d over 2z. And when the x is small compared to 1, there's a famous approximation to the binomial that 1 plus n times x. And I'm going to use that. And I'm going to use that for those two binomials. I'll think of the first binomial as 1 plus negative d over 2z. And the power will be negative 2. And I'll use this so-called binomial expansion. So E is qk hat over 4 pi epsilon 0 z squared. Okay, for the first binomial, I'll have 1 plus n, negative 2, and the quantity x is negative d over 2z. That's applying the binomial approximation to the first binomial. Then I have minus. Now I'll apply the binomial approximation to the second binomial. I'll use curly brackets. 1 plus n negative 2 times x d over 2z, close curly bracket, close square bracket. Now I got to look very carefully at the pluses and minus signs. I've got a plus 1 here. Whoops, I didn't mean to erase it. There we go. I've got a plus 1 here and a minus 1 there. Now let's look carefully at this next. I've got 3 minus signs multiplied together. So let's see what that is. Well, that's negative d over z. All that. Okay. I do beg your pardon. I made a sign mistake. It's 1 plus, right? Look here. 1 plus nx. So 1 plus negative 2 over times negative d over 2z. It's really important that the signs are right. So that becomes plus d over z. All right, then I've got a minus times a minus, 2 times d over 2z, so plus another d over z. So what is that altogether? Well, let's see. It's k q hat over 4 pi epsilon 0 z squared 2d over z. Okay, but the 2 there can take part of that 4. There's a z squared and a z downstairs. So I end up with q times d times k hat over 2 pi epsilon 0 z cubed. Okay? And that's the resulting expression that we want to use. And that's what I've got written right up here. Q times d times k hat over 2 pi epsilon 0 z cubed. Directed, as our picture shows over here, the net field is directed, because that's positive, in the plus z direction up there. So we have a formula for calculating the electric field on the symmetry axis of a dipole if we're in a place where the z coordinate of the point is much larger than the distance d between the points. And we will use that when that condition is true. Now the last thing is just to point out something that's convenient, to define a new quantity, because we find it convenient. And because you can actually measure this property of atoms and molecules. We're going to define a new quantity called electric dipole moment. It's a property of an electric dipole. The symbol for electric dipole moment is a lowercase p with an arrow on top. Sorry that that's the same symbol we use as linear momentum. It doesn't mean that at all. So the context here, if you're working with two equal and opposite point charges, you know you're working with an electric dipole, and you see the symbol little p, then you have to be able to say, oh, well, they mean electric dipole moment. And so here's my picture again of the dipole. Positively charged particle, plus q. Negatively charged particle, negative q. Distance d between them. We're going to take a unit vector, n hat, dimension 1, has only one job, to point in a particular direction. What particular direction? Pointing from the negative charge to the positive charge. In this case, that would be pointing up. All right, here's the definition of electric dipole moment vector. Take the magnitude of either charge, q, times the distance between them, d, times that unit vector, n hat. And so you get a vector that points from the negative towards the positive charge and would be labeled p arrow. Note the SI unit of electric dipole moment is Coulomb times meter. If we use that definition for this case, and remember the z-axis goes vertically up, the n hat's the same as k hat. So for this dipole, P arrow is Q, D, K hat. Ah, but wait, that's part of what in my formula up here for the electric field. Right? There's a Q times D times K hat in the numerator. So a very compact way to write the electric field on the symmetry axis and far from the dipole is there. E equals P arrow, electric dipole moment vector, over 2 pi epsilon 0, and then we'll just call it r cubed. And r means the distance from the center of the dipole, let's look over here, to the point P, right there. Because it doesn't have to be the z-axis. All right, so this will be handy. But note when it's valid. This result is only valid on the symmetry axis of the dipole, like right there in this drawing, and far away, which in this drawing would mean r is much, much greater than d. R, remember, goes from the center of the dipole out to point P. Note that the field magnitude far from the dipole drops off with the distance as 1 over r cubed, not 1 over r squared. A dipole doesn't act like a single point particle, right? The field of a point particle goes like 1 over r squared. The field of a dipole goes like 1 over r cubed. It's weaker. Because the contributions from the two particles, contributions to the electric field from the two particles nearly cancel out. Nearly, but not entirely. And this result is more useful than you might first guess, especially in atomic and molecular applications. All right, so the last thing I'm going to do here is give you a class engagement exercise to do on Blackboard. With some practice thinking about the electric field of an electric dipole. Okay, so this one is all about, this practice is all about the electric dipole and looking at the electric field on the symmetry axis. So again, let's be clear what we mean. I'll draw it like this. Plus Q separated from minus Q by a distance d. I'll draw the distance over here to the side. And the symmetry axis is the line that goes straight through them like that. And I will go back to calling this the z-axis, okay? All right, so when it says on the symmetry axis of the dipole, we mean on that red dashed line. So here's the first question for you to answer. On the symmetry axis of an electric dipole, at points above the positive charge, meaning here on up, how does the direction of E compare to the direction of little p, the electric dipole moment? Same direction or opposite direction? Are E and P in the same direction when you are somewhere up here, or are they in opposite direction? That's question one. Question two, on the symmetry axis of an electric dipole at points below the negative charge. So now you're somewhere down here, okay? How does the direction of E compare to the direction of little p? Same direction or opposite? So now you're down below there and you're asking, how does the direction of E arrow compare to the direction of P arrow? And then the third question, let's pick a point P1 that's a far distance Z1 along the dipole axis from the dipole center. Okay, far away, it's a distance Z1. That's point P1. Point P2 is at a distance 2Z1, twice as far along the dipole axis. What is the ratio of the field magnitudes, ET over E1, at the 2 points? The point 2 and then point 1. Okay? So those are the questions I wish for you to answer on Blackboard. And that's all for this video lecture.